So we have a bowl modeled by the curve y equals 3 natural log of x minus 6 rotated around the y-axis within the bounds of 0 to 4. This bowl is filled with 1 meter of a liquid which has a density of 840 kilograms per meter cubed, and we would like to find the work required to pump this 1 meter out of the bucket. We're going to be using 9.8 meters per second for gravity. So this is a pretty complicated problem, and I think that the first step here is to create a diagram that represents the situation we're dealing with so that we can start applying some of our intuitions about calculus and solve this problem. So I'm going to start out here by just drawing an xy coordinate graph where this x-axis is y equals 0, and we have an upper bound of y equals 4. Now, the actual graph of y equals 3 natural log of x minus 6 is kind of an irregular graph. I'm just going to approximate it somewhat like that. And what this question is asking us is to rotate this around the y-axis and create a rotational solid that we've been told is hollow and is a bucket. And what we can do from here now to calculate the volume of a shape such as this is we can think of this as a series of disks, where each disk is within the actual bucket and has a height change y. Now we know that the volume of any cylinder is pi times the radius squared times the height. So in our situation, the volume of this specific cylinder, this disk within the bowl, is equivalent to pi times the radius, which at any point of this function, the radius from the y-axis to the function is the y value of that function. So we know that it's equal to pi times the function squared times some change in y. Okay. Now, because we're dealing with this in terms of y, and we're looking at changes in the y value, we first need to re-express this equation in terms of x. So let's go ahead and do that over here. So we're starting out with y equals 3 times the natural log of x minus 6, which we can then convert to y over 3 equals the natural log of x minus 6. And if we take both sides and express it as e raised to the power of the contents, it looks just like this. And what this enables us to do is to cancel out that natural log, as e to the natural log is just 1. So we have e to the y over 3 equals x minus 6, which then can be converted to e to the y over 3 plus 6 equals x. So what this means is that for any disk within this bowl, the volume of that disk is equivalent to pi times e to the y over 3 plus 6 squared times some change in y. Now, why did we find this value? Well, yes, we do have some volume, but what this question is asking for is for us to solve the work required to pump the liquid out of the bucket. So in order to do so, we should first start with finding the force, as force is a component of solving the work. So the force in this situation is the mass times the acceleration. And what that means for us is that equals the mass times 9.8, which is what we were given for the approximation of the acceleration of gravity. Now we don't actually have a mass right away, so I'm going to use the given density in order to solve for the mass. So we know that density equals mass over volume, so that means that mass can be expressed as density times volume. Or in other words, we have the density, 840 kilograms, times our volume that we calculated earlier, which is pi times e to the y over 3 plus 6 squared times some change in y. So what we found is that the force equals 9.8, the acceleration, times 840, the density, times the rest of the expression for volume, which is pi times e to the y over 3 plus 6 squared times some change in y. Okay. So now that we have force, we're going to continue onward and try to find out what the work is. And what's important to understand is, while this is an expression for force at some given point, It also can be viewed as a function of force, as we're looking at any change in y. So we could say that f of x, the function for force, is equivalent to this value. So what we're going to do now is we're going to solve work by creating an integral that looks at the distance remaining. So if we know that the total height of this space here is 4 meters, then at any change in y, the height is going to be 4 minus y, right? So let's put this all together now. We have the height, right? And we have our force. So we have that work equals force times distance. And in our case, it's moving vertically, so that's a height. So we have that the work equals our force function times 4 minus y. And the sum from looks like 0 to 1, because that's the work that we found to move this right here. Okay, so now that we have this, I'm going to go to the next page, and we're going to start trying to solve this integral, because it's going to require quite a bit of integration by parts, and I want to kind of go over another method called the tabular method for integration by parts, and hopefully we can save some time by multiplying these together in a more efficient way. Okay, so now that we've expressed our work as an integral of the function of force times the change of distance, we're going to actually place our function of force into the integral and start simplifying things to get ready for integration. So we have that work equals the integral of 0 to 1 of 840 kilograms per meters cubed, or it might have been foot cubed, times 9.8 meters per second, times pi, times e to the y over 3 plus 3 squared times some change in y. And notice that now we're in the integral, that this change of y can just be expressed as dy, our typical way of denoting changes of some variable that we're integrating in respects to. So I'm going to go ahead and write a dy over here. Now we're going to move to our distance, which is 4 minus y for any point on the graph. So I'm going to go ahead and add that right here, just as we had before. So this is our total function. And if you notice, this entire component of the integral is actually a constant. And because it's being multiplied by the rest of the contents of the integral, we can actually comfortably remove it outside of the integral. And for the sake of saving space in the rest of this video, I'm going to use the character alpha to denote 840 times 9.8 times pi. So now that we have this, we can say that the work is equal to alpha for the integral of 0 to 1 times e to the y over 3 plus 3 squared times 4 minus y. Okay, so before we go any further, I think that we should probably expand out this binomial into its corresponding polynomial. So work equals alpha, integral of 0 to 1, for e to the 2y over 3, using the properties of exponents to multiply this 2 times y over 3, plus 9, plus 6 e to the y over 3, plus 9, times 4 minus y dy. So, how do we solve a problem like this? Well, there's actually quite a few ways to do this. You could separate this into a series of separate integrals where each term of this expression is its own integral. You could distribute this second half right here to the rest of the contents just by FOILing it all out. But I'm going to use a method called the tabular method. And this is just a way of expediting the process of integration by parts by looking at integration by parts in a different way. So we know that to evaluate some function in the form u dv, it equals u times v minus the integral of v du. And this is a pretty great formula. It's a product of the product rule. And it can really be used here to deal with something like this where we have a complicated problem. Now the question is, which part of this are we going to choose for the value of u, and which of this is going to be the value of dv? And for that, there's a really helpful little mnemonic device called liate. And what each letter stands for in this, or it's rather an acronym, and each letter in this stands for a different type of mathematical expression. So this part right here is like logs. This is inverse trig functions. This is algebra. This is trigonometric functions, and this is exponents. And notice out of our two terms here, we have something that has exponents and something that is relatively algebraic. And what this means is that we can comfortably assume that the value for u should be this part, and the value for dv should be this part. So, with that in mind, I'm going to set up my tabular system. So I'm going to start out by writing sine. Next is going to be a column for u. And finally, for some dv. And the idea behind this is that for every value in u, for each time you go down a cycle and follow this order of signs, you differentiate. And for each time you go down a cycle for dv, you integrate. So let's go ahead and put what we said u and v in dv are. I'll write those up here for later reference if we need to. So we have 4 minus y. We have e to the 2y over 3 plus 6e to the y over 3 plus 9. We're going to use this rule right here now to simplify this process. We could kind of do u substitution for each one of these terms, but we know that if we have e to the power of some variable divided by a constant, what we'll see is the repetition of that term and the constant taken out front. So I'm going to go ahead and do this. So remember, for this one we're going to differentiate, and for this one we're going to integrate. So I'm going to do this in red. So the derivative of 4 minus y is negative 1. And if we integrate this, we should get 2/3 e to the 2y over 3 plus 18 e to the y over 3 plus 9y. So that 18 came from 3 times 6, and this 2/3 was multiplied to the outside, following this rule again. So now I'm going to do the next step in a separate color. The derivative of negative 1 and the derivative of any constant is 0. And the integration of this is going to be a little messy. We're going to take this out again, so we're going to have 4/9 e to the 2y over 3 plus 54 e to the y over 3 plus 9y squared over 2. This is a really ugly problem. I'm sure there are permutations of this problem that are a lot easier to manage. So hopefully we can get through this without making any arithmetic issues or algebra issues. So once we've kind of set this up, we want to stop whenever we see a term that equals 0 in the differentiation column of u. Because what this means is that for any term, it's not going to matter, as if we multiply its corresponding integration, it's going to equal 0. And the way that this graph works is that the sign is applied to the term directly to the right of it, right? And then when we look at what's being multiplied, we go diagonally. And while this doesn't seem very intuitive in nature, this actually makes a lot of sense if you expand upon the formula of integration by parts. But I'm going to keep this problem focused on solving the value for that work today, and I'm just going to go ahead and use this principle. So from this, we have that 4 minus y times 2/3 e to the power of 2y over 3 plus 18 e to the power of y over 3 plus 9y. And then we're going to look here. minus times negative 1 is just a positive 1 times this. So we're just going to add, so plus 4 over 9 e to the 2y over 3 plus 54 e to the y over 3 plus 9y squared over 2. And for each one of these terms, we're going to evaluate within the bounds of 0 to 1. And that is how you use the tabular method to convert an integration by parts problem into its proper antiderivative. So this is a very gnarly problem. This is going to require a lot of foiling, a lot of term combination, and finally when we do evaluate the function, we're going to have to remember that whenever we see this 0, we have to take it into consideration as e to the power of 0 equals 1, and we'll end up with actual constants. So I'm going to go ahead and start a new page, and hopefully we can get something done here by slowly foiling this out and actually solving the problem now. And I also want to remind everyone that this whole value is multiplied by our value of alpha, which is described up here. So I'll see you soon. Okay, so now that we're on a new page here and I have some room to work this problem out, let's start by first foiling out this 4 minus y times its other term. So the way I like to do this is very sequentially, and I think that for most people this is kind of the way of doing this. So I'm going to start with the 4. So we have 4 times 2, which is 8/3. I'm actually going to write a little higher here. It's going to be a big problem. 8/3 e to the 2y over 3 plus 4 times 8, which is, or 4 times 18, which is, I believe, 72, hopefully. 72 e to the y over 3 plus 36y. So that's the results of multiplying 4 to each one of these terms, which is great. Now let's do the negative y. And you'll probably notice this will create some uglier terms, but when we actually evaluate within the bounds of 0 to 1, it won't be so bad. So we have minus 2/3 y e to the 2y over 3 minus 18y e to the y over 3 minus 9y squared. Okay, now we're going to add the rest here, so plus 4 over 9 e to the 2y over 3 plus 54 e to the y over 3 plus 9y squared over 2. Okay, so first thing we want to do is combine like terms. There's a lot of them, and we can actually save ourselves a lot of time by working this out. So I'm going to grab my calculator for adding some of these fractions quickly. They're not all the easiest. So let's see here. As far as e to the 2y over 3, we have this term, we have this term, and I believe that's where it stops. So 8 over 3, that's 4/9, is 28 over 9 e to the 2y over 3. We're going to do y divided by 3 now. So plus, we have 72 and 54. Looks like that's it. It's going to be 126 e to the y over 3. Next up is going to be ye to the 2y over 3. There's only one of them, and same thing for just ye to the y over 3, so we're just going to write both of these terms. So minus 2/3 y to the ey, or e to the 2y over 3, minus 18y e to the y over 3. Okay. Then we have positive 9/2 y squared minus 9y squared. So that's equal to negative 9 over 2 y squared. Now we'll get rid of both of those. And finally, 36y. So let's go ahead and write that. Great. All right. So this whole function, again, multiplied by alpha, evaluated from 0 to 1. Or rather, this is on the inside of here, before alpha is distributed. Evaluated from 0 to 1. So, let's start doing it. Let's start plugging in the values of 0 and 1 here. It's going to be a long process. Okay. So, 28 over 9 times e to the 2/3 plus 126 e to the 1/3 minus 2/3 times 1 times e to the 2/3 minus 18 times 1 times e to the 1/3 minus 9 over 2 times 1 squared, which is just 9 over 2, plus 36 times 1, which is just 36. So that's our 1. Okay? And that's all going to be minus 28 over 9 times e to the 2 times 0 divided by 3, so this is just times 1, plus 126 to the 0th, which is 126, minus 2/3 times 0, this whole thing is 0 right here, 18 times, again, 0, minus 9 over 2, that's 0, and that's 0. Okay? This value can be condensed once again, so we have 126, negative 18, and negative 2 divided by 3. This is going to be, and plus 28 divided by 9. This is 995 over 9. Oh, sorry about that. No, it's not. This is 322 divided by 3. One second here. 126 minus 18. Alrighty. That's 108 e to the 1/3. And then 28 divided by 9 minus 2 divided by 3 equals 22 over 3, or 22 over 9. E to the 2/3. I'm going to mark which ones I'm dealing with here. Sorry about that. These two are just being condensed into this term, and these two are being condensed into this term. Finally, we have 36 minus 9 divided by 2, which is just, let's see here, 63 over 2. So that's both of those turned to that. Okay, so we're starting to get somewhere. I'm going to write this all out nice and pretty since it's starting to get a little messy. So we have alpha times 108 e to the 1/3 plus 22 over 9 e to the 2/3 plus 63 over 2. So this is a number. We did it. We found a number. This can be evaluated, and we can actually figure out what the value of work is. And this is a lot of work to find this work. Okay, so I was editing this video, and I realized that I failed to include this number right here in our final expression for work. So I'm going to go ahead and rewrite this with that value in mind. So we're going to have that work equals alpha times 108 e to the 1/3 plus 22 over 9 e to the 2/3 plus, actually in this case it's going to be minus 1757 over 18. So this is an actual number. I mean, I kind of said that before, and I want to emphasize now that we can get a real value for this. We can find the value for work required to move that 1 meter of water out of the bowl in joules by multiplying this value we just expressed times the value that we declared as alpha, which is 840 pi times 9.8. So we have work equals 9.8 times 840 times pi times 108 e to the 1/3 plus 22 over 9 e to the 2/3 minus 1757 over 18. And I'm going to just plug this into my calculator now, and we get a final value that the work required is 1,496,769.5226376 joules. Alright, thank you for watching throughout this entire video, and feel free to ask me any questions you have about this process, and I'll see you next time.